So here's our compound. We've got this cyclic structure with a nitrogen in it. That's referred to as an N-heterocyclic. This ring is actually called aromaticity. It's the fact that there is a double bond at each position, but you can only draw one resonance form at a time, and the double bonds all move around. And then we've got this. What types of groups are you expecting to find based on this compound? Well, I know this is not your typical benzene ring, but it's like an analog of a benzene ring. And so I would expect these hydrogens coming off of this ring to show up in that same region, 6.5 to about 8.5. That's the chemical shift I'd expect them. So 1, 2, 3, 4. How do I know there's no hydrogen on the nitrogen? It's not shown. It has to be shown for it to be there. It's a hydrogen, or a nitrogen. And then I've got these two H's, CH2. Do you suspect that this is more alkane, functional group adjacent, vanillic, aryl, or carboxylic acid aldehyde? What functional group do you think it's adjacent to? Yeah? Two hydrogens on a carbon that is bonded to an alcohol. Is that it? Is that the only functional group it's adjacent to? What? I heard it. Think. Yeah, it's adjacent to that ring. If this were benzene, that would still be a functional group. It's like a type of benzene, so it's still a type of functional group. Exactly. So the fact that this is adjacent to two functional groups means, first of all, notice how it's close to an alcohol, or excuse me, close to an oxygen, just like the example we see here, hydrogen, carbon, oxygen. I'm expecting it to already be on the far left side of this range. That's the nuance of the table I've created. Then the fact that it's next to a second functional group makes me think I'm probably going to see it at the end of this range, maybe even beyond this range. That's the problem with these functional or these correlation tables. There is this intrinsic hand waviness to it. Oh, the signal didn't show up exactly where you thought it would based on these dotted lines. That's okay. It's not meant to be hard cutoffs, but like, you know how we say orbitals are 95% probability region? This is like 95% the probability region of where you're going to find that signal. So let's look back at its spectrum. Oh, and then the OH. Where is the hydrogen of the alcohol? Where do you expect that to show up? Notice that I actually don't have OH of an alcohol on here. But we talked about this last class. Where do we expect this hydrogen to show up? Yeah, it's this weird range where it overlaps alkanes, functional group adjacent, and vanillic hydrogens.
With that one that's connected to the two functional groups, is that a situation where there's that compounded effect that we were talking about?
Exactly.
So would you expect to see like pretty far down that because it's two main like functional groups or not?
So it's a good question. For example, the hydrogen signals from CH3Cl, chloromethane, those show up about here on the right-hand side of the functional group adjacent range. Dichloromethane, CH2Cl2, those signals show up further to the left still. Maybe, I actually don't know that number exactly, maybe in the range we'd expect, maybe beyond the range. But you can see that by just adding one more halogen, the hydrogen signals are shifting left. But chloroform, or trichloromethane, its signal shows up at 7.26. And I know that one by heart because it's a very common solvent in NMR, so its signal shows up all the time. And so you can see that 3 functional groups got it that far left. Here, I would expect the alcohol and the ring is probably going to put these signals maybe around 5. That's where I'd be expecting it. Beyond functional group adjacent, kind of in the vanillic region. So let's check it, shall we? And Kira, you gave this to me because you felt like it did align with the correlation table, or just because you liked it? All right, so let's see how it looks. I've got signals from 6.5 to 8.5. Those must be my aryl hydrogens. That's this, 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 this. Good. I expected those to be in that range, and I found signals there. And then these 2 hydrogens, I said, would probably be on the far end of the functional group adjacent, maybe even beyond it. And I see something there. And we said that the hydrogen of the alcohol should be in that, maybe in that similar region. So right now, I can't, with any certainty, tell you which of those signals belongs to which. That's not what we're looking at right now. We're just considering how the chemical shift tells us something about the bonding nature that those hydrogens are in. Tells you a little bit about the functionality of it. To be fair, if I gave you this and you didn't know the molecule that it corresponded to, I think you should be able to look at it and say, this part of my correlation table tells me I have an aromatic ring. This part of my correlation table tells me I might have an alkene. I've got something functional group adjacent, but I can't really tell you with certainty if there is actually an alkene and what the functional group is. Couldn't tell you if it's an alcohol, an ester, an ether, a halogen, nothing like that. Just tells you there's something that's pulling electrons away, something that's de-shielding that hydrogen. Questions on this? What questions do you have on this? Anybody else want to look at their structure because they feel like it really aligns well or it really does not align well? Okay. Then I want to move into the second major component of analyzing an NMR spectrum. I guess let me just remind you, first we looked at the chemical shift. Now we're looking at the integration. Hydrogens that are in the exact same bonding environment are considered identical to each other. Remember that the signal that's produced is based on how that hydrogen nuclei is being shielded or de-shielded with respect to the groups around it. And so if 2 hydrogens or 3 hydrogens are all in the exact same environment, they're going to produce the same signal. In fact, one thing that we can try to look for in certain molecules is unique sets of signals. Like here, I would say this is 1 signal, 2 signal, And then we've got clearly 3, 4, and 5. It looks like we've got 5 sets of unique signals. If we, and I shouldn't have erased it, if we actually look at the molecule again though, 1, 2, 3, 4, 5, 6 unique hydrogens. The CH2, those are identical to each other. They're both attached to the same carbon. They're attached the same distance from the alcohol, the same distance from the ring. Those are the same hydrogen environment. They're identical hydrogens. They produce one signal. The hydrogen of the alcohol, that's its own hydrogen. That produces one signal. And then notice how in the ring there is no symmetry. This hydrogen is unique. This hydrogen is unique. These two hydrogens are unique. And I can prove it by just describing where they are. A hydrogen next to the nitrogen and the substituent. A hydrogen close to the nitrogen, a hydrogen close to the substituent, and a hydrogen in between the two of them. They're all different from each other. So there is this issue with unique hydrogen sets. Sometimes hydrogens that are different from each other still produce the same signal, or they produce a signal in the same range. And so their signals overlap with each other. I can't ask you to guess. I won't ask you to guess which of these signals is overlapping with each other. We know that it's some of those aryl hydrogens that are overlapping because we felt pretty confident one of these is the hydrogen of the alcohol, one of them are the 2 hydrogens of the CH2. But I should have had 4 signals in the aromatic region, and I only had 3. So you can look at a compound and predict, this is how many unique signals I think I will have. And you will not always find that. You will often run into this issue where signals overlap with each other. And actually, SDBS is really nice, and it tells you this hydrogen at A, next to the nitrogen and the substituent, shows up at 8.4, and this hydrogen at B, next to the nitrogen, 8.3. Those are overlapped. These 2 hydrogens next to the nitrogen. And then hydrogen C, next to the substituent, 7.7. Hydrogen D, in the middle of everything, 7.2. So there are instances where you might be asked to decide how many unique sets of hydrogens are here. And you can give a theoretical answer. It doesn't mean it's always going to experimentally show up that way. I want to give you an idea of what I'm talking about. Has anybody started on this yet? PLO Chem 4. Once again, required bonus points. You can't lose any points for doing this. But not my material, so it looks a lot different than what I will expect you to be able to do in this unit. For instance, this is a simulated spectrum, I believe, not necessarily an experimental spectrum. So it looks a lot different than the ones I'm going to show you most of the time because it's not a real spectrum. But here's a question. I just want to go through one of these with you. How many different sets of equivalent hydrogens are found in the following compounds? Let's take this molecule here, and let's work through this together. How many equivalent hydrogens in this molecule? How many sets of hydrogens? Why don't you guys take 30 seconds, try to figure out how many sets are identical to each other, and then we'll walk through it together. I'll zoom in on it so we can see it a little bit more clearly. Yeah, feel free to discuss with each other. Okay, ready? How many sets of hydrogens here? How many groups of identical hydrogens in this molecule, 1,4-dimethyl cyclohexane? 3? Natalie, did you raise your hand? No? Anybody get something different than 3? Anybody get 3? You got 3?
I can't decide between 3 and 6.
3 and 6. Those are big numbers. Okay, let's start here. Methyl group, CH3. Are all of those hydrogens identical? Yeah, they're on the same carbon, so they're all identical to each other. This is not always true. We'll get to that. What about this CH3? Identical to this or not? We should be able to show a plane of symmetry if they are identical. We should show a plane of symmetry that reflects them onto each other. And I can see a plane of symmetry there, so they are identical. We can also describe it. A methyl attached to a tertiary carbon attached to secondary, secondary, tertiary. Methyl attached to tertiary, secondary, secondary, tertiary. Identical. Okay, so the methyl groups are one signal. What about the hydrogen here at the tertiary carbon? Are these hydrogens identical to each other? Also, yes, they're reflected by that same plane of symmetry. What about this CH2 and this CH2? Are they identical to each other? Yeah, they are. But these are actually related by a different plane of symmetry. This plane of symmetry reflects them into each other. And this plane of symmetry reflects these CH2s into each other, which means this CH2 is identical to this, is identical to this, is identical to this. So that's methyl, tertiary, secondary. That's just 3 sets of hydrogens because of the planes of symmetry in the molecule. So the conversation we had last week talking about chirality, looking for symmetry in the molecule, especially with meso compounds, it really feeds in well here because you can look for symmetry in a molecule and decide how they're related. Now there are some odd examples. For instance, let's look at this compound, 1-butene. The CH3 is unique. The CH2 is unique. The CH of the alkene is unique. But what surprises many is that the CH2 is actually 2 unique hydrogens. This compound has 5 total sets of hydrogens. Why? That CH2, they're attached to the same carbon in the same way that this CH2 is attached to the same carbon. So why are these different? Well, you can actually see it based on how they're spaced out. This hydrogen is very close to this hydrogen that I numbered number 3, whereas this hydrogen is very far away from that hydrogen I numbered 3, in the same way that this hydrogen is close to this CH2 group, and this hydrogen on top is far from that CH2 group. They are in different places in space, despite being attached to the same compound. Another way of putting this, the CH2 here has rotational freedom. It can rotate around this sigma bond, and it can rotate around this sigma bond. But you cannot rotate around a pi bond. It breaks a pi bond. So these two hydrogens, because they're always rotating, they always experience the same chemical environment at some point through that rotation. But these two hydrogens cannot rotate. So they don't experience the same chemical environment. They experience a unique chemical environment. That's the one distinction here, is that CH2s on alkenes behave a lot different than what you might expect. Unless, of course, there's symmetry. Those CH2s are symmetric to each other because of the plane of symmetry in the molecule. So, 9 times out of 10, it's asymmetric. But there are instances where it is symmetric. So it's nice to take a problem like this and say, how many signals should I expect to see? But that guess does not always reflect into what you actually see. I expected 6, I saw 5. And this is where the value of integration comes in. Any math fans in here? Tell me what integration is. Integration is the opposite of differentiation. Yep. It's a mathematical function. Although, even if you're not in math, you probably have used integration before in a sentence, or you've heard integration used before. Could you give me an example of what integration means outside of math? Yeah. You want to integrate your life. You're trying to bring things together in your life so that you've got balance, right? And this actually relates to its mathematical term. Integration is to take everything that's underneath a curve and report that area as one sum. Integration is the area under the curve. In this case, our curve is our signal. So we're saying area under the signal. But we've got this issue, remember? Hydrogens that are all identical produce the same signal, and sometimes signals overlap. Here's the beauty of having integration. Integration is proportional to, I think that's a math term, that little symbol. If you don't want to write that symbol, you can write it out. Integration is proportional to the number of hydrogens producing a signal. Back in the old days, they had to print out an NMR spectrum and cut paper to the shape of the curve and calculate manually the area of the curve. Today, you just click a button and the computer auto integrates. And sometimes you have to go in and move the boxes around to make sure it integrates better, because when I integrate this, I don't want it to integrate from here to here. That might be adding some area that I don't want. Instead, I want it to start right where the curve begins and end right where the curve stops. That's the area that I want. I want all of this area because that signal is being produced by my hydrogen or my hydrogens. So this is something that I will give to you on an NMR spectrum. And if you want to see what it looks like, I've got the midterm from the summer posted under the midterm module. There's NMR questions on there. You can always head there and see what they look like. But if I were to give you this example, this is what it would look like. Actually, I don't really do this. I take the entire aromatic region and I integrate it at once. Because I'm not going to have you decide what signal comes from what. I would rather you actually think of the aromatic region as just one region of signals. This integrates to 4. Oops. Right at the good part. Now you might have already looked to see, but which of those other 2 signals do you think will integrate to 1 and which will integrate to 2? Because remember, the only thing we're missing is the OH hydrogen and the CH2 2 hydrogens. On this one, you can kind of tell. One of the signals is like about twice as tall. And so you can say pretty easily, this integrates to 2H, this integrates to 1H. It is not always that clear. Because when we get to the third thing, not chemical shift, not integration, we're actually going to find out that these signals can get wider, which lowers them. And the integration stays the same. To try and visualize that, this has the same area as this. One is taller and narrower, one is shorter and wider, but they have the same area underneath the curve. That's okay? So you're not looking for the height of the signal. You're not looking at the intensity on the y-axis. You're not saying, wow, this is a lot taller than this, so I know they're integrations. You have to be given those integrations in order to make that assumption. Actually, this is a good example. This integrates to 2. Look at how much shorter it is than this signal. But it's much wider. This integrates to 1. This integrates to 1. They're not even the same height. And this also integrates to 1. It's not the same height either. Active uses a different way to show integration. Because integration is kind of a mathematical function, we can show integration with this sloped line. So on active, instead of giving you these numbers like I'm going to give you, actually I think I'm just going to sketch this so that you can kind of see the comparison. We're just looking at these 2 signals on the right, the shorter one, the taller one. I'm going to give it to you as 1H, 2H, so you know the area underneath those curves. And why am I putting H? It's the number of hydrogens producing that signal. So I'm literally telling you 1 hydrogen here, 2 hydrogens here. Active shows it like this. Those curves are the integration. which is a mathematical function. But it's saying that this signal has about this much height rather than this signal whose integration is twice as tall. It doesn't give you a number, it gives you a ratio. About half, about twice. And that's because integration, where did I put it? Integration is proportional to the number of hydrogens. And the computer doesn't know how many hydrogens are there. So the computer will pick one signal and it will normalize that integration to 1. Regardless of if there's 1 hydrogen producing that signal or 18 hydrogens producing that signal. It just normalizes it to 1. So here's the thing. Based on these curves, this could be a 1 to 2, a 2 to 4, a 3 to 6. There's no way of knowing. Unless you have the chemical formula handy, and then you know how many total hydrogens you have to work with anyways. And then you can figure out what makes the most sense. So if we were looking, again, with active on this, oh, I made a mistake, yeah? This is what the integrations would look like. It tells us each individual signal just by height. It's not quite, you know, a 2 to 3 ratio, because a 2 to 3 ratio would be like more like this. But this is about half the size of the other one. So it could be 2 to 1 to 1 to 1 to 2. Could be 4 to 2 to 2 to 2 to 4. I'm not trying to make it that hard. I'm going to give you the actual ratios. But this is what I mean that the integration is proportional to the number, proportional to the number of hydrogens. It's any of those possible ratios. All right, I want to do another molecule so that we can try to compare this. If I were to give you just the integral values, I want you to try and figure, or just the integral shapes. I want you to try and figure out what their values probably are. Oops, sorry. This is hard. I know that's not incredibly clear, but see there's 4 signals. This one, these 2. As you think about what the possible ratios could be, consider their relative heights. Which of them look twice as tall as the others? Which of them look 3 times as tall as the others? Which of them look a third as tall, 2/3 as tall? Now, consider that we have this chemical formula. What do you think the chemical, what do you think the integrations are at each of these signals? Why don't you guys spend 5 minutes in your groups discussing how you can break those 9 hydrogens up to provide integrations for these signals, okay? Assign them with these like 1H, 2H, 3H, 4H type stuff. Yeah. Are you able to come up with a set of integrations that add up to 9? You got it? Tell me what they are from left to right. 1H, 2H, 3H, 3H. That's 3, 6, 9. Good. And this peak, or this integration, was meant to be about half the height of this integration, and about a third the height of these other integrations, although I don't know if I was quite there at a third. Which means that this signal was meant to be about 2/3 the height of these taller ones. It feels so arbitrary, doesn't it? And the thing is about active giving you these types of problems, I can't really change it, but computers don't even give it to you that way anymore. So I'm not sure who they're trying to please by writing a question that looks like that. I think it's very possible, actually, that your textbook does it this way, too. I just don't know because I haven't looked at the textbook problems in a long time. And that they show it to you with these lines. But I mean it when I say computers will show you these lines, and they will give you calculated values that you can shift as you want to be these numbers. In fact, when you do an experimental one, the computer is doing real math. So you get something that's more like 1.001 to 2.16 to 2.97 to 3.10. I don't know why I went to such different numbers, decimal places. The computer gives you real numbers, at which point you have to have a little bit of a wavy hand to say 2.16 is not 2, but it's close to 2. 2.97 is not 3, but it's close to 3. 3.10 is not 3, but it's close to 3. And you round it. Or if you want to, you can tell the computer, change what you're actually measuring in your integration to try and make these numbers better. But I have never, ever seen a computer give an integration that had only whole numbers. Experimentally, it's just not what happens. It doesn't mean that the math is breaking physics or like conservation of mass or anything like that. It just means it's hard to get good, clean data. But you're not going to get data like this. You're not going to get data like this. I'm going to give you data like this when I test you on this. Now, I want to talk about how we use this to go backwards. If we have the integration of a signal we can try to build what components of the structure we think we have. And I'm going to use this example to show you guys. This isn't going to go in a specific order. Instead, it's going to go by the most common things you see. If you have a signal that integrates to 3H, this is often telling you that you have something in your molecule bonded to a CH3 group. It is quite possible that you actually have a CH2 group and a CH group that are overlapping and adding to one signal. And that sucks for you. But most of the time, it's a CH3 group. It is, most of the time. On that same thread, a 2H group, this is often a CH2 group bonded somewhere in your molecule. Do you remember what we said R stands for? The rest of the molecule. And really the only option that R cannot be right now is H. It could be an oxygen, a nitrogen, a carbonyl, a ring, another carbon group. But if it's H, then we're actually just looking at what's above, right? The CH group, or excuse me, the 1H group, this also simply tells you you've probably just got a CH group bonded to 3 different things in your structure. What those 3 things are, I couldn't tell you, but you've got a lone hydrogen. Those are very common. Here are common duplicates. A 4H integration often means that you have some kind of symmetry in your molecule. You've got 2 CH2 groups that are identical to each other, adding up to the same signal. Where do you think I'll go from here? 6H. With whatever you want in the middle, but 2 methyl groups that are symmetric to each other, all 6 of those hydrogens integrate together. On a similar thread, 9H. Nine H is pretty often what is that group? Tert-butyl. A tert-butyl group has 3 methyl groups, all attached to the same carbon, which means all 9 of those hydrogens are identical to each other. I already told you that vinyl or vanillic hydrogens are kind of weird in the ways that they look. Like they can be attached to the same carbon and still give different signals. Sometimes the 2 hydrogens attached to the same carbon give such different signals, and a hydrogen on the other alkene carbon overlaps with one of the other 2, where you don't even get 3 unique signals, and it's not these 2 who seem more similar to each other overlapping. It's actually this odd man out overlapping with one of them. You get these weird combinations. It's kind of hard to give any sort of rule for the aromatics, but, or excuse me, the alkenes. But for the aromatics, the aryl hydrogens, if you're looking in this region, 6.5 to 8.5 most often, a 5 hydrogen integration Remember, not all 5 of those hydrogens are the same, so they're likely to produce more than one signal, although they don't always produce more than one signal. They sometimes overlap completely. Which is why I'm not going to give you aromatic regions where each peak in the aromatic is integrated on its own, but I'm going to integrate the aromatic region. So if the entire aromatic region integrates to 5, regardless of how many signals that is, that means you've just got a mono-substituted aromatic ring. If the integration in the aromatic region integrates to 4H, there are actually a number of different things that can be happening here. Those 4 remaining hydrogens can be arranged in several different ways. You guys agree? And the challenge here comes in deciding how are they arranged. This is where it starts to get out of our depth here. If you want to learn more about how to look at an NMR signal to decide what of those dye-substituted structures you have, you should take a spectroscopy course. Shameless plug. In the spring, I'm teaching Chem 1250, where we'll be doing Introduction to Instrumental and Chemical Analysis. It's a 4-credit class, Friday afternoons from 1 to 6 p.m. 4-credit class, though. That's 4 hours. No, that's 5 hours. 2.5 hours of lecture, 2.5 hours of lab. Anyways, we will be diving into NMR, although to be honest, probably not even that in depth. We'll actually be diving more into how the NMR works and how to interpret signal, and we'll be looking at different NMR spectra that you can get out, not just proton, not just carbon, but cozy, depth, things like that. It will be a good time. So if you need 4 credits and you have a free Friday, come on over. The only thing I'm going to say about this is that this 1,4 substituted ring actually gives the cleanest signal. This often looks like this. 2 signals with 2 peaks each. It looks very clean. The other ones are super messy. So if you're ever in the aromatic region and you see 4 hydrogens, integration of 4, and it looks nice and clean like that, you've got that 1,4 substituted structure more than likely. The other ones, they're going to look super messy and hard to tell apart. Do I need to go on? 3H, there's 3 aromatic hydrogens, 3 groups coming off. 2H, 2 aromatic hydrogens, 4 groups coming off. It's less and less likely that you see tri-substituted rings and tetra-substituted rings. It's never 0, but it's just not common. Sound good? So I want to come back to this structure we were looking at. We had 1H, 2H, 3H, and 3H. And I want to build from this integration. I know that I've got 4 pieces to this molecule. I've got a CH group. I've got a CH2 group. And I've got 2 CH3s. I want to put those CH3s on either side, pointing other directions, because this is a linear structure, right? If you don't believe me, I gave you the chemical formula. We can do degrees of unsaturation, 0 degrees of unsaturation in this molecule, a linear structure. Now, I could try to guess at how those are put together. And there's actually a few different ways that I could put all four of those pieces together. No, actually, I might be lying. There might not be. Yeah, no, there are. There are several ways. Because there is a piece missing. This is what we know from integration. But it was from the chemical formula C4H9Cl that we know there's actually one other piece. A piece that doesn't show up on the proton NMR. What is that piece? The chlorine. Notice how I've got my 4 carbons. I've got my 9 hydrogens, but chlorine is not here. So there is this other piece that NMR does not tell me. Does NMR tell me the carbons? No. That's where we're building it. NMR tells me the hydrogens, and we're assuming they're bonded to carbons. Oh. Well, what if they're not bonded to carbons? What if a 2H group is actually an NH2 group? Or what if a 1H group is actually an OH group? Those are things I'd like you to add, actually. I'd like you to go back and say, we can't always be confident that a 1H hydrogen is definitely bonded to carbon. It could be bonded to an oxygen. It could be bonded to a hydrogen, a secondary amine, or a secondary amide. This could be an alcohol or a carboxylic acid. We would know the difference by the chemical shift. This could be an amine or an amide. We actually wouldn't know the difference by the chemical shift necessarily, but these are other ways that I can get 1H integrations. Does that track? Do you guys agree? Alcohol gives 1H, secondary amine, 1H, primary amine, 2H. These are things that you might be able to look for if you know the chemical formula. But you wouldn't actually know if they're bonded to carbon or some hetero atom. So there are several different ways that I can piece together these 5 pieces. For instance, what if I have CH3 connected here and CH3 connected here? That leaves CH2 connected here. But CH2 needs 2 connections. So the last connection would be out to the chlorine. But I could have also had CH3 connected here, Cl connected here, CH2 connected here, and then on the other side of the CH2, the remaining CH3. That's structural isomerism. I'll kind of demonstrate what I just said. That's one option. And that's another option. This is 2-methyl-1-chloropropane, also called isobutyl chloride. 2-methyl-1-chloro, well, I said that wrong. 1-chloro-2-methylpropane. And this is 2-chlorobutane. Those are structural isomers of each other. And I think those are the only 2 structural isomers you could get based on these integration values. So how would we know which one we're actually looking at? Is that the best NMR can do? The best it can do is tell us, well, it's one of these 2 structural isomers? No. Take a 5-minute break and I'll tell you how we can figure out which of these structural isomers we have. All right? 5 minutes, even if you're not going to leave. Get up, move around, get your blood flowing. Yeah, you know what those are? Arrows. Nuclear spin arrows. Combinations of nuclear spins. All right, guys. Do you remember when we introduced NMR? The foundation of what we said NMR works with? What it's looking for? So the magnetic field interacting with the nuclear spin. Yep. And I gave you this crude idea of the nuclear spin all align. Think of them as just pointing whichever which way, and then they all align, and then they go back down to their ground state. I like that idea because I think it's helpful for me to think about how every hydrogen's got a different kind of environment that it's in, and again, that shielding and de-shielding that nuclei experience impacts how they interact with the magnet. It turns out that when they get aligned, they oftentimes, have these combinations of alignments. And the way that hydrogens on one carbon align can actually impact the way that neighboring hydrogens experience the magnetic field. So here we're getting into point 3, which is called multiplicity, also called splitting pattern. And this is to explain why some of the signals you've been seeing are not showing up as a nice little line out of the baseline giving me a signal, but instead they're showing up as these messes, sometimes with all of these peaks. Why does a signal have multiple peaks? Why does it split into these multiple peaks? Signals have one or more peaks. I'll be honest, when I was learning NMR and then also done learning and just applying it, I kept confusing these terms, signal and peak. A signal is where the baseline is left and then returns. And everything in between, all the little ups and downs before coming back to baseline, those are peaks on the signal. So earlier you sketched two signals, one was taller than the other. Those were both singlets, they had just one peak to the signal. It turns out that the number of peaks a signal will have is equal to n plus 1. Oh, sorry. N is neighboring hydrogens. We do not go too far to consider neighboring hydrogens. We only look on carbons adjacent to the carbon of which the hydrogen of interest is located. One carbon away, that's as far as you can go. No further. Hydrogens will impact each other's signals up to one carbon away. And there is an important caveat on this. OH I should say OH and NH. That goes for NH2 as well. But these hydrogens bonded to O, hydrogens bonded to N. Do not experience or add to N. So how many peaks would an OH signal always have? N is always 0. They don't experience N. They don't count as N. Those hydrogens on oxygen always have one peak. NH and NH2 as well. The hydrogens producing a signal from NH or NH2, they don't have neighboring hydrogens. They don't count as neighboring hydrogens. So those signals always show up with one peak. It's with the carbon groups where we get more complicated. So let's make a list. If n equals 0, then we get a signal with one peak. And we call this a singlet. If a carbon has, if a set of hydrogens has one neighboring hydrogen, there will be two peaks. And this we call a doublet. If a set of hydrogens has two neighbors, you will see three peaks, but those peaks are not all the same. Here, why did I say 3? I'm sorry. 2. If n is 2, my bad. Here we're looking at 3 hydrogens, CH3, in this molecule, CH2Br, CH3. So we're looking at the signal that these 3 hydrogens make, and they have how many neighboring hydrogens? This is such a weird way to write it. On the adjacent carbon, 2 hydrogens. The spin of those 2 hydrogens could be spin up both times, spin down both times, or one spin up, one spin down, 2 different ways. And these 3 different alignments of the neighboring hydrogens impact how these 3 hydrogens experience the magnetic field. You'll see here that we're saying the magnetic field is applied, and now we're looking at the magnetic field of the protons, because spinning charged particles create magnetic fields of their own. And if those magnetic fields are aligned opposite, opposed the other way, then it turns out we get a greater chance of the neighboring hydrogens. This is so weird. The neighbors dictate the shape of your signal. We get a greater chance of the neighboring hydrogens being out of phase with each other, right? Out of alignment more often, and that impacts the shape of the signal more. In alignment, in different ways, having different impacts on your signal less often. So you do not get 3 equal peaks. Instead, you get a small, big, small peak, a little crown. And we call this triplet. Let's look at the other way. These 2 hydrogens on the CH2, how many neighbors do they have? 3. These neighbors, they impact each other. So you should always be able to analyze an NMR and say, well, if I'm seeing that this signal has 3 peaks and that it has 2 neighbors, then I should find 2 neighbors somewhere that have 3 neighbors. And when n equals 3, the number of peaks equals 4. And here we get some symmetry back, because those 3 neighbors can be all aligned one way or all aligned the other. Or one is out of alignment with the others, and again, where 2 of them are always spin up. Or one of them is always out of alignment with the others, and again, but 2 of them are always spin down. Those alignments make different impacts on the signal. And so you get these equal chances in the middle, twin peaks, and these equal chances on the outside that are less often, twin peaks. So you get this shape, small, tall, tall, small. And we call this a quartet. For anything larger than this, n equals 4 plus, the signals can get pretty complex. And we often refer to them as multiplets. Of course, you'd have a quintet, a sextet, a septet, an octet, a nonet. But with increasing peaks, these exterior signals, they get smaller and smaller and smaller until, to a certain point, your magnet might not actually be strong enough to even pick up on that signal. It gets really hard to even see that it's there. This is splitting pattern. It is the shape of the signals. So I want to reiterate the three components that we've analyzed about NMR. Chemical shift, where along the x-axis. Integration, how many protons are making that signal. Splitting pattern, the shape of that signal, which is impacted by the neighbors. Where, how many, and what shape. That's what we're looking at with NMR. So let's go back to this compound, 2-chlorobutane. Oh, no, I didn't say that. Isobutyl chloride, 1-chloro, 2-methylpropane, or, because we don't know yet, sec-butyl chloride, or 2-chlorobutane. We don't know which of these it is yet, because we had determined these two possible structures based on integration alone. We hadn't considered splitting patterns. Would these have different splitting patterns? Yeah. And actually, I guess we could have, yeah, I guess you probably could have argued that it was never going to be this one anyways. Because we knew that we had two different CH3 groups. But those two CH3 groups, they're actually identical to each other. They're not different. They're attached to the same carbon. So they would give one signal that integrates to 6H, not two different signals integrating to 3H. But you know what? We were just piecing together our puzzle. We were just checking. So that's a fair thing to do. And now that we've done it, we should realize it was never going to happen anyway. Which means this is really the only structural isomer we could have predicted. So let's prove it. Let's prove that these hydrogens give the splitting patterns we would expect. There's two ways that we can do this. I want us to take the NMR and extract information about splitting pattern and neighbors. So I'm going to call these peaks A, B, C, and D. And by the way, if you want to have this in your notes so that you can reference this, we are looking at the H1 NMR for 2-chlorobutane. How many peaks do you see on A? Six? 1, 2, 3, 4, 5, 6. I wouldn't be mad at you if you said 4. And if you weren't sure what these were, that's fair. So it's either 4 or it's 6. If it's 4, how many neighbors? because 4 peaks has 3 neighbors. But 3 neighbors, and remember that A is a 1H group. 3 neighbors would be just a CH3. And we know that our, boy, I really screwed it up. We know that our 1H should have a CH3 group and a CH2 group next to it. How many neighbors is that? 5. 3 plus 2. This CH. Because remember, the integration of A is 1H, 2H, 3H, 3H. So it makes the most sense to say this is probably 6 peaks. N equals peaks minus 1. 5. How do you get 5 neighbors? There's really only one way to get 5 neighbors. Here is my CH group. To get 5 neighbors, I must have a CH3 on one side and a CH2 on the other. What goes here? Don't look at the answer. Anything but a hydrogen. Good answer. And because we know the chemical formula, we know it's the chlorine, but also we know something more. What goes here has to be, actually not anything but a chlorine. We need to add anything but a hydrogen and a carbon group with hydrogens, because that would add more neighbors. If it was CH or CH2, can't be that either. We know that this signal needs to be shifted all the way down to 3.9. What is going to shift that down to 3.9? Some functional group. For right now, that's all we know. Does that seem valid? That's why the hydrogen signal is so far left, because it must be functional group adjacent with these 5 neighbors. All right, signal B integrates to 2H. So we know we're looking at a CH2 with 2 groups. How many peaks on this? Oh man, this is where experimental data really bites you in the butt. Notice how these peaks actually overlap. Peak B and, signal B and signal C, they actually overlap with each other. I'm only telling you the integrations because I know it. But if I was on a software on a computer, I would have a hard time separating them. The computer can actually do some math to try and separate them. But otherwise, they would integrate together to 5H. But let's see if we can find how many peaks. It looks like I've got a small one here. 1, 2, 3, 4, maybe a small one here, 5. If I had 5 peaks, would you agree that with the odd number of peaks, I would expect the 5th one to be the tallest? Just like how 3 peaks, the center is the tallest and then the others are even. And I think I see that here. It looks like this center peak is the tallest. These other 2 aren't evenly aligned. That's what you get with experimental data, that hand waviness. So it looks like I've got 5 peaks. How many neighbors? 4 neighbors. Peaks minus 1 gives us n. I'm going to spell that out a little bit more. N equals peaks minus 1. How do I get 4 neighbors? There's 2 ways. I could have CH2 and CH2. Those are 4 neighbors. But I already believe that this CH2 is this CH2. So one of my neighbors is a CH. How do I get the other 3? A CH3. I'm starting to get pieces of my molecule, and right now, these 2 pieces overlap with each other. I've actually built my whole molecule, but I can prove the rest of it. Signal C, how many peaks? Well, we accredited this small one to signal B, which means I'm actually just looking at these two giant peaks. 2 peaks. How many neighbors? 1 neighbor. What would that look like? I'm looking at a CH3 group that's bonded to what? A CH. Since we already know that this is the molecule we're looking at, can you tell me now, signal B, is it produced by the methyl group on the left or the methyl group on the right? The methyl group on the left. The methyl group next to the CHCl because of the splitting pattern, but also a little bit because of its chemical shift. Which of the methyl groups is closer to the halogen? The one on the left. And which of the methyl groups has a signal that is further left, closer to the functional group adjacent region? Signal C, the methyl group on the left. All of these pieces are starting to line up, the chemical shift, the integration, and the splitting pattern. Signal D, how many peaks? This one's much more clean. 3 peaks. 1, 2, 3. How many neighbors? Who are those 2 neighbors to this CH3 group? Well, it can only be a CH2. So we said these pieces overlap. So I know I have a CH2. Now it turns out this piece overlaps with this piece. So I know I have a CH2 to CH3. And this piece overlaps with this piece. So I have a CH3. And then from the chemical formula, the only other thing that I was missing was my chlorine, the explanation of why the 1H signal is the furthest left signal. And here's what I'm going to do. This belongs to A. This belongs to B. This belongs to C. And this belongs to D. Or if you want to see it here, A, B, C, D. What do you think of that? NMR is an incredibly powerful tool. We literally just built a molecule based on interpreting the signals from NMR. The chemical shift, the integration, the splitting pattern, all tie in with each other. So I want to give you guys an opportunity to practice this. I'm going to pull up an NMR spectrum, and I'll give you the chemical formula. I want you guys to spend the rest of today trying to solve for this structure. And when you've solved it, you're free to go. In the last couple of minutes of class, if you haven't solved it, I'll walk through how to solve it. This is chemical formula. C3. Sorry, I didn't do the math first. H6O2. That's a small molecule. Yeah? And here is the integrations. 1H. 2H. 3H. Use your correlation table to make sense of the chemical shift. Use integrations to build pieces of the structure. Use the splitting pattern to try and connect those pieces of the puzzle. I'm here to answer questions. If you guys get through this fast enough, I'll put a different one up there. When we come back next week, we're looking at IR first, and then mass spec, and we'll try to wrap all of it up. But I want to remind you guys, this concept is section 13 homework. So it's actually the homework. I still haven't fixed the due dates. If anybody would actually remind me about that with the message, I would really appreciate it. This is the stuff that has a later due date now, but I want you to do it now because it's, you would agree, right? It is harder to take in. It takes a little bit more time. Do you want to move closer? What do you want? The numbers on the bottom? Or the number of lines? I agree. 2H? I'd say 4 as well. Looks like a quartet. 3H? Sure. Oh. Honestly, I always forget about that. No, at least I just talked about that yellow graph. But you can see how it's like way more detailed. Almost like too detailed. How does the whole... Yeah, yeah. Well, then notice how most of those overlaps are like all functional group adjacent. Yeah. So what does it help? Oh. Yeah, I agree. So wave your hand a little bit and try to figure out what else would even be possible. Like what? Remember, these aren't hard, fast regions. Yeah, it makes more sense that it would be that way than the other side. Word to the wise, calculating degrees of unsaturation will give you a hint of how you need to combine pi bonds and rings to try and make sense of a structure. Are there any degrees of unsaturation in here? That is important to know. If there's no pi bonds, you want to know that. If there are pi bonds, you want to know that. Or if there's a chance at rings, you want to know that. So I might start with degrees of unsaturation. What's the rule? 2 chicken. 2 chicken rule. looked like it was sealed for you. Yeah. Yeah. I tell them that it's allowed. I tried to reverse search it. Oh, yeah, yeah. Twice the number of carbons. Minus the hydrogen. Minus the halogen. Plus the nitrogen. Plus 2. No, it's not. And then divided by 2. So, no. 6 minus 6 plus 2. Divided by 2.
Okay.
There you go. No. You got 2 times 3 is 6. Plus 2 is 8. There's 2 chicken rule. You gotta add twice. You'll multiply by 2. You'll add by 2. The only thing you don't do is subtract by 2. Don't second guess yourselves. Remember to squint and shake your head if things don't look like they're in the right spot. I think you got too many carbons there, didn't you? Oh, no, you don't. No, sorry, I didn't see that it was an OH group. This looks to me like you've got 3 1H groups and 1 CH3 group on the left. Do you agree? 1H, 1H, 1H. And this is just a 3H with only 1H, which would be a doublet 3H and not a triplet. You agree? Okay. Yeah, I did. And going for a ring's not a bad idea, but you know, there's a lot of different ways that a ring can be in there. So you gotta just play around with it. Okay. Well, from this idea, this is what we got from that earlier one. But do you really think there's potentially 2 CH3s in this molecule? No, I agree. I think there's really only a chance for 1 CH3. So it seems more like these are the groups we got, right? And this, because there is a 2H signal. And now we got to try and figure out how these connect. Like, is the CH2 connected to the CH? Is the CH2 connected to the CH3? How would those splitting patterns tell us that? Look at this, D. When you've got the 2H signal, how many peaks do you have? Based on that, how many neighbors does that CH2 group have? You gonna solve it? You proved it by Googling it? Okay. Really close. Really close. Here's the only issue with it. This CH2 being bonded directly to this C, its chemical shift is not going to be 4.25. Its chemical shift would be more like 3.0. Remember the correlation table? You have to add it. That's okay. On the correlation table, when we look at the functional group adjacent, the carbon bonded to a carbonyl is usually more on the right-hand side. But a carbon bonded, a hydrogen bonded near an oxygen is more to the left-hand side. So these 2 hydrogens, they wouldn't show up this far left, 4.25, unless they were bonded to an oxygen. And then the other thing is, you showed OH, which is an carboxylic acid, which shows up in the same region as an alcohol. And so you're like in the ballpark, but actually it's ester. I'm actually we'll have to go through it right now. Yeah? You got it. Great work. All right, you guys ready? Two chicken rule gave us how many degrees of unsaturation? 1. We do not know if that is a ring or a pi bond. We don't know if that pi bond is a CO double bond or a CC double bond. There's a lot of structural isomers here. We see a 1H signal at 8. What is supposed to show up at 8? Aromatic hydrogens. There cannot be aromatic hydrogens. I don't have enough carbons for an aromatic ring. So either this is an alkene hydrogen that is in a really weird spot, or it's an aldehyde or carboxylic acid hydrogen that's in a really weird spot. Then I've got a CH2 and a CH3. This CH2 is a quartet, which means that it has 3 neighbors. And this CH3 is a triplet, which means that it has 2 neighbors. These groups are neighbors to each other. So my structure for sure has a CH2 and a CH3. I've got 2 oxygens to work with here. The fact that my CH2 is so far left, keep in mind that this is like almost to the edge of our functional group adjacent range. The fact that this is so far left tells me that that CH2 is most likely bonded directly to an oxygen group. 4.5 is about the edge of this, and we're at 4.25. So I think that this is bonded directly to an O. And I still haven't used up my pi bond. And I have 1 carbon and 1 hydrogen and 1 oxygen remaining. So, carbonyl aldehyde. Here I've got the 1H of an aldehyde. It is unexpectedly out of range for an aldehyde. It's much lower than you'd think it would be. But that's the only thing that makes sense. Some of you might have gotten to this structure. CH3 and CH2 are still neighbors. This is still unexpectedly out of range, so it seems feasible. The only thing that's different is that the signal of the CH2 would end up being further to the right. It would have been closer to the right-hand side of the functional group adjacent, because that's what our correlation table tells us. Groups that are more to the carbonyl side, further to the right. Groups that are more to the oxygen side, further to the left. This is ethyl formate. What we're looking at is a molecule called ethyl formate, or ethyl methanoate. The structural isomer, propanoic acid, the only difference is the chemical shift of the CH2 and probably the chemical shift of the OH. Challenging. It all came down to just the chemical shift of the CH2. All right, try your hand at the section 13 homework this weekend. I'm going to set its due date to Monday night. So I want you to try and be done with it mostly by Monday, and we can ask questions in class Monday to try and finish it up. All right? And I'll see you guys on Monday to talk about infrared spectroscopy. Have a great weekend.